black holes are dying, every single one of them, including the supermassive monster at the center of our galaxy. The math showed that black holes slowly leak energy, shrink over time, and eventually vanish completely. This wasn't just surprising, it was catastrophic for physics, because the same calculation proved that when a black hole dies, it takes with it every piece of information about everything that ever fell inside. A star, a planet, a person, gone without a trace. Quantum mechanics says that's impossible. Information cannot be destroyed. It's one of the most fundamental rules in physics. So either Hawking was wrong or quantum mechanics was wrong. 50 years later, we still don't fully know which one it is. But what we've learned trying to figure it out has completely transformed our understanding of space, time, and reality itself. To understand why that discovery was so devastating, you need to understand what black holes actually are, not the Hollywood version, but the real thing. A black hole is not a hole. It's not empty space. It's the opposite of empty. It's a region where matter has been compressed so densely that the gravitational field overwhelms every other force in the universe. The escape velocity, the speed you'd need to travel to get away from the surface, exceeds the speed of light. Since nothing moves faster than light, nothing leaves. Not particles, not radiation, not information. The boundary around this region is called the event horizon, and it's not a physical surface you could touch, it's a mathematical boundary. A point of no return, the concept traces back to 1915 when Einstein published general relativity. Within weeks, a German physicist named Karl Schwarzschild found an exact mathematical solution to Einstein's field equations while serving on the Russian front in World War I. His solution described what would happen to space-time if all the mass of an object were compressed into a single point. Space-time would curve so severely that it would form a one-way membrane. Schwarzschild died months later from a disease he contracted at the front, never knowing that his solution would become one of the central objects of 20th century physics. For decades, physicists treated the Schwarzschild solution as a mathematical artifact rather than a physical prediction. Einstein himself published a paper in 1939 arguing that black holes couldn't actually form in nature. He thought the collapsing matter would stabilize before reaching the critical density. He was wrong. In 1939, the same year Einstein published that paper, Robert Oppenheimer and Hartland Snyder showed through careful calculation that if a star is massive enough, nothing can stop the collapse. Not electron pressure, not neutron pressure, not any known force. The star collapses all the way down to a singularity, a point of infinite density, and a black hole forms around it. Oppenheimer would go on to lead the Manhattan Project. This paper was largely ignored in the chaos of the war years. The concept remained obscure until the 1960s, when a new generation of physicists started taking it seriously. Roger Penrose in 1965 proved something definitive. Using a mathematical technique called topology, he demonstrated that once a collapsing star crosses a certain threshold, the formation of a singularity is mathematically inevitable. You can't avoid it. Einstein's equations guarantee it. This was the first rigorous proof that black holes weren't just theoretical curiosities. They were real consequences of the laws of physics as we understood them. Penrose would eventually receive the Nobel Prize in Physics in 2020 for this work. John Wheeler, The great American physicist started calling these objects black holes around 1967, though he didn't invent the term. Before that, they were called frozen stars, or completely collapsed gravitational objects. Wheeler had a genius for naming things and for identifying what was important. He gathered some of the brightest young physicists around him at Princeton, set them to work on black hole problems, and the results transformed physics. One of those young physicists was Jacob Bekenstein. In 1972, Bekenstein was a graduate student, and he was thinking about a deceptively simple problem. The second law of thermodynamics says entropy never decreases in a closed system. Entropy is a measure of disorder, of the number of possible microscopic arrangements compatible with a given macroscopic state. When you heat a gas, its entropy increases because the atoms can occupy more possible states. Entropy is nature's bookkeeping system for disorder. Now imagine you take a hot cup of coffee full of entropy and drop it into a black hole. The black hole swallows it. From outside, that entropy appears to have vanished. The total entropy of the universe has decreased. That should be impossible. Bekenstein proposed the radical solution. Black holes must have entropy themselves. When the coffee falls in, the black hole's entropy increases to compensate. The books stay balanced, but for a black hole to have entropy, it had to have a temperature. And for an object to have a temperature, it has to radiate energy. But black holes can't radiate anything because nothing escapes the event horizon. The whole point of a black hole is that nothing gets out. Bekenstein's idea seemed self-contradictory, and Hawking, then one of the most respected young theorists in the world, set out to demolish it. What Hawking found instead was the most important result in theoretical physics of the 20th century's second half. When you carefully apply quantum field theory to the curved space-time near a black hole's event horizon, something extraordinary happens. The quantum vacuum is not empty. Empty space is not actually empty. Quantum mechanics fills it with constantly appearing and disappearing pairs of virtual particles, a particle and its antiparticle, flickering in and out of existence for moments too brief to violate energy conservation. Near the event horizon, something different happens. One particle of such a pair can fall inside the event horizon while the other escapes. To an observer far away, it looks as if the black hole is emitting real particles. The black hole is radiating. The temperature of this Hawking radiation is inversely proportional to the black hole's mass. For a black hole with the mass of the Sun, the temperature would be about 60 billionths of a degree above absolute zero, far too cold to ever detect against the background glow of the cosmic microwave background. But the principle is real. As a black hole radiates, it loses mass. As it loses mass, it gets hotter and it radiates faster. Eventually, in a sequence that takes an inconceivably long time for large black holes, it evaporates completely. A solar mass black hole would take about 2 times 10 to the 67th years to evaporate. The current age of the universe is about 10 to the 10th years. These are not objects disappearing anytime soon. But here's the problem that has haunted physics ever since. When particles fall into a black hole, they carry information. A book falling in carries the information of its text. A star falling in carries information about its temperature and structure. Quantum mechanics encodes all of this as the quantum state of the infalling matter. When Hawking radiation escapes, it's perfectly thermal. It's random radiation characterized only by the temperature. It carries no information about what fell in. So when the black hole finally evaporates completely, all that information is gone. This is the black hole information paradox, and it represents a direct collision between the two greatest theories in physics. General relativity and quantum mechanics have coexisted uncomfortably since the 1920s. In everyday regimes, they don't need to interact. General relativity governs the large scale, the curvature of space-time, the motion of planets and galaxies. Quantum mechanics governs the microscopic, the behavior of particles, the structure of atoms. They use completely different mathematical languages and rest on completely different conceptual foundations. For most purposes, you can use one or the other without worrying about the other, but black holes are the place where both must apply simultaneously. You need quantum mechanics to understand the radiation and the physics of infalling matter. You need general relativity to describe the curved space-time. And when you try to use both together, they give you the information paradox. The paradox became the central problem of theoretical physics for the next 5 decades. It drove the development of entirely new theoretical frameworks. It led to the holographic principle, string theory's greatest successes, the AD-CFT correspondence, and new ideas about the nature of space-time itself. Everything we'll discuss from here comes downstream of that single calculation Hawking did in 1974 while trying to prove Bekenstein wrong. Through the 1970s, while theorists were wrestling with these implications, observational astronomers were accumulating evidence that black holes actually existed. The evidence was always indirect because you can't see a black hole directly. What you can see are its effects. The most productive method was X-ray astronomy. In 1962, a rocket carrying Geiger counters detected an intense source of X-rays from the constellation Scorpius. This was the beginning of X-ray astronomy. The source, called Scorpius X1, turned out to be matter being heated to millions of degrees as it fell toward a neutron star. But more interesting objects followed. Cygnus X1, discovered in 1964, was different. A blue supergiant star was orbiting an invisible companion. The companion's mass, calculated from the orbital dynamics, was too large for any known compact object other than a black hole. At least 10 solar masses packed into a region smaller than Earth. The scientific community debated for years. Alternatives were proposed, but every additional observation tightened the case. Cygnus X1 became the first widely accepted black hole candidate. The X-ray binary systems, as these were called, became laboratories for studying extreme physics. Material from the visible star is pulled toward the black hole, forming a swirling disk called an accretion disk. As the material spirals inward, it rubs against itself, heats up through friction, and radiates powerfully. The temperature of the innermost part of the disk can exceed 10 million degrees, emitting X-rays. By studying these X-rays, astronomers could learn about the black hole's mass, spin, and the structure of space-time near the event horizon. The measurement of black hole spin became possible through careful spectroscopic analysis. As X-rays from the hot inner disk illuminate the cooler outer regions, a characteristic spectral line from iron atoms appears in the spectrum. This line is smeared and distorted by the Doppler effect from the orbiting gas and by gravitational redshift as photons climb out of the black hole's gravitational well. The exact shape of this smeared iron line reveals how close the innermost disk extends to the event horizon. A rapidly spinning black hole allows the disk to extend closer, producing a different line shape than a slowly spinning one. Through this technique, astronomers have measured spins of stellar mass black holes across the galaxy. While stellar mass black holes were being catalogued through X-ray astronomy, evidence was building for a completely different class of object. Supermassive black holes, millions or even billions of times heavier than the Sun, were apparently lurking at the centers of galaxies. The clues came from studying active galactic nuclei and quasars. Quasars, discovered in 1963, were the brightest objects in the universe, outshining entire galaxies while being concentrated in regions smaller than our solar system. No known physical process could produce that much energy from such a small region except one thing: matter falling into a supermassive black hole. The physics of quasar emission is remarkable. When gas falls toward a supermassive black hole and forms an accretion disk, it doesn't just produce heat. The efficiency of energy conversion is extraordinary. Whereas nuclear fusion in stars converts about 0.7% of mass into energy, the accretion of matter onto a spinning black hole can convert up to 42% of mass into energy, according to some calculations for maximally spinning Kerr black holes. This is the most efficient energy source in the universe. A quasar consuming a few solar masses of material per year can outshine every star in an entire galaxy. The evidence for supermassive black holes in the nuclei of ordinary galaxies, not just the exotic quasars, accumulated through the 1980s and 1990s. Our own Milky Way became the prime test case. At the center of our galaxy, in the direction of constellation Sagittarius, there is something called Sagittarius A. Radio observations showed a compact, powerful source of radio emission. Infrared observations, which can penetrate the dust that blocks visible light to the galactic center, revealed stars orbiting something in the very center. Two independent teams, one led by Reinhard Genzel at the Max Planck Institute in Germany, one led by Andrea Ghez at UCLA, spent years tracking the individual orbits of stars near the galactic center. These were exhausting, painstaking observations, tracking the same stars year after year with the best infrared telescopes on Earth. What emerged was astonishing. One star, designated S2, was completing a full orbit in just 16 years, swinging around an invisible central mass at speeds exceeding 5,000 kilometers per second. That's almost 2% of the speed of light. From the orbital period and size, you could calculate the mass of the central object as precisely as you calculate the mass of the Sun from Earth's orbital parameters. The answer was 4 million solar masses concentrated in a region smaller than the orbit of Mercury. Nothing but a black hole could be that massive and that compact. In 2020, Genzel and Ghez shared the Nobel Prize in Physics for this work. Their decades of careful observation had turned the concept of galactic black holes from plausible inference to established fact. But there was still something missing. Despite all the indirect evidence, nobody had ever directly imaged a black hole. Nobody had seen the event horizon. All the evidence was circumstantial, derived from the black hole's effects on surrounding matter. To actually see a black hole requires confronting a fundamental imaging challenge. The apparent size of the event horizon of Sagittarius A as seen from Earth is about 50 microarcseconds. An arcsecond is 1/3600th of a degree. 50 microarcseconds is tiny beyond ordinary comprehension. It's equivalent to trying to read a newspaper on the surface of the moon. No single telescope on Earth could achieve this resolution. The resolution of a telescope is limited by its aperture, the size of its collecting area. The larger the telescope, the finer the detail it can see. To resolve Sagittarius A, you'd need a telescope roughly the size of the Earth. This is what the Event Horizon Telescope accomplished. Not by building a single Earth-sized telescope, but by linking together 8 existing radio observatories scattered across the planet, from Hawaii to Chile to Spain to Antarctica. By precisely timing observations from all sites using atomic clocks and combining the data using a technique called very long baseline interferometry, the collaboration created a virtual telescope with a baseline equal to Earth's diameter. The resolution achieved was sufficient to image the shadow of a supermassive black hole. The technical challenges were staggering. Radio telescopes record raw voltage from electromagnetic waves. The signals need to be combined with phase coherence, meaning you need to know exactly when each signal arrived at each telescope to within fractions of a nanosecond. Each observatory collected petabytes of data onto hard drives that were then physically shipped to central processing facilities. The data was combined using sophisticated correlation algorithms, a process that took months. Then the challenge of making an image from the correlated data required yet more mathematical sophistication. The Event Horizon Telescope cannot make images the way a conventional camera does. A camera records light at every point simultaneously. The Event Horizon Telescope records interference between pairs of telescopes, giving information about brightness at particular spatial scales. Turning this sparse set of measurements into a complete image is an inverse problem with many possible solutions. The team developed multiple independent imaging algorithms and verified that they all converged on the same result. They also simulated thousands of possible astrophysical scenarios to check that the result was consistent with a black hole and not some alternative source structure. On April 10th, 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow. The target was the supermassive black hole at the center of galaxy M87, 55 million light-years away, with a mass of 6.5 billion solar masses. The image showed a bright ring of emission surrounding a dark central shadow. The ring was hot plasma orbiting the black hole. The shadow was the region where the black hole's gravity prevented light from reaching us. One side of the ring was distinctly brighter than the other, exactly as predicted by general relativity. The side where the orbiting plasma was moving toward us appeared brighter due to relativistic Doppler beaming. The image confirmed that Einstein's theory of gravity worked correctly even in the most extreme gravitational environment we could observe. Measuring the size of the shadow and comparing it to the mass estimated from stellar kinematics provided a powerful test of general relativity. If gravity deviated from Einstein's predictions near the black hole, the shadow would be the wrong size or wrong shape. Within measurement precision, everything matched. The universe was behaving exactly as Einstein said it should. This was simultaneously triumphant and slightly disappointing, because a deviation from general relativity would have pointed toward new physics. But confirmation of a century-old theory at the extreme limits of its validity was still extraordinary. In May 2022, the Event Horizon Telescope released the image of the second target, Sagittarius A, the black hole at the center of our own galaxy. This should have been easier, because Sagittarius A is thousands of times closer than M87's black hole. But proximity created its own problem. Because Sagittarius A is smaller and less massive than M87's black hole, plasma orbits it in minutes rather than days. The image changes on timescales comparable to the length of a single observing session. It was like trying to photograph a violently flickering candle by combining exposures taken hours apart. The team developed new techniques to account for this variability, averaging over many possible source configurations that were consistent with the data. The resulting image again showed a bright ring and dark shadow, consistent with general relativity predictions. Two black holes imaged directly, both matching theory. The era of black hole imaging had begun. While the imaging effort was unfolding over years of preparation, another revolution in black hole astronomy was proceeding on a completely different front. This one involved not light at all, but gravitational waves. Einstein predicted gravitational waves in 1916, almost immediately after completing general relativity. Accelerating masses, his equations showed, would create ripples in space-time itself, propagating at the speed of light. But he also calculated how weak these ripples would be, and concluded they would never be detectable. He was nearly right. It took a century of technological development and some of the most violent events in the universe to prove him wrong. The story of gravitational wave detection is one of the most audacious scientific projects in history. Joseph Weber at the University of Maryland built the first gravitational wave detectors in the 1960s, large aluminum cylinders meant to ring like bells when a gravitational wave passed through. He claimed detections in 1969, but no one could reproduce his results, and most physicists concluded he had been fooled by various sources of noise. Weber's failure was not a failure of the concept, but of the technology. He was at least a generation ahead of what was achievable. The correct approach suggested in the 1970s and developed through the 1980s and 1990s was laser interferometry. The idea is elegant. You build two long arms arranged in an L shape and send laser light down each arm. Mirrors at the ends reflect the light back. You then combine the two returning beams and look for interference. If a gravitational wave passes through, it stretches space in one direction and compresses it perpendicularly, changing the length of one arm relative to the other. The laser light takes slightly different amounts of time to travel the two arms, creating an interference pattern that reveals the distortion. The problem is sensitivity. A gravitational wave from a black hole merger 1 billion light-years away would distort space-time by less than 1 part in 10 to the 21st. That's like measuring the distance to the nearest star to within the width of a human hair. To achieve this, you need lasers more powerful and more stable than anything previously built. You need mirrors of surpassing optical perfection. You need isolation from seismic noise, from thermal fluctuations, from acoustic vibrations, from the quantum noise of the laser light itself. You need arms long enough that tiny fractional changes in length produce measurable absolute changes. LIGO, the Laser Interferometer Gravitational Wave Observatory, was built with 4-kilometer arms at 2 sites in the United States, one in Hanford, Washington, and one in Livingston, Louisiana. The 2 sites are separated by 3,000 kilometers, which means a real gravitational wave signal would arrive at both sites with a time delay of at most 10 milliseconds, the time it takes light to travel between them. A coincident signal at both sites provides compelling evidence against locally generated noise. The initial LIGO detectors ran from 2002 to 2010 without detecting gravitational waves. This was expected. The detectors were not yet sensitive enough for likely astrophysical sources. A major upgrade program called Advanced LIGO rebuilt the instrument from the ground up with more powerful lasers, better mirror coatings, improved seismic isolation systems, and sophisticated techniques to reduce quantum noise. Advanced LIGO came online in September 2015 with roughly 3 times better sensitivity than the original instrument. On September 14, 2015, during the very first observing run of Advanced LIGO at 09:50:45 Unitel-TIE, both detectors registered a signal. At Livingston, the signal arrived 7 milliseconds before Hanford, consistent with a source in the southern sky. The signal was a chirp, a rapid sweep upward in frequency lasting about 0.2 seconds, followed by a merger spike. The waveform matched precisely the expected signal from 2 black holes spiraling together under gravitational wave emission, merging and ringing down to a final quiescent black hole. The analysis revealed the source. 2 black holes, one of 36 solar masses and one of 29 solar masses, had orbited each other in a death spiral lasting millions of years. In the final fractions of a second, they were circling each other hundreds of times per second, moving at significant fractions of the speed of light. When they merged, they formed a single black hole of 62 solar masses. 3 solar masses, equivalent to 3 entire suns, had been converted to pure energy and radiated as gravitational waves in less than a second. The peak power output of this event exceeded the combined luminosity of all the stars in the observable universe. The LIGO collaboration spent months verifying the detection before announcing it publicly in February 2016. The scientific community's reaction ranged from celebration to astonishment. The first direct detection of gravitational waves confirmed a century-old prediction of general relativity. It proved that binary black hole systems exist and merge in the universe. It opened an entirely new channel for astronomical observation. Rainer Weiss, Barry Barish, and Kip Thorne received the Nobel Prize in Physics in 2017. The detections kept coming. Each one told a different story, different masses, different spins, different distances. In August 2017, LIGO and its European counterpart, Virgo, detected gravitational waves from 2 neutron stars merging. A gamma-ray burst was detected 2 seconds later. Optical telescopes found the counterpart and watched it fade over days, observing the signatures of heavy element synthesis. Gold, platinum, and many other heavy elements were being forged in real time by neutron star collision. The multi-messenger era of astronomy had arrived. The accumulated population of black hole mergers detected by LIGO and Virgo has revealed something unexpected. Before these detections, stellar evolution theory suggested that stellar mass black holes would mostly be between about 5 and 20 solar masses. Black holes above about 50 solar masses should be rare or absent because the stars massive enough to produce them would lose too much mass in stellar winds before collapsing. There's also a predicted gap in the black hole mass distribution called the pair instability mass gap. Stars massive enough to produce black holes heavier than about 50 solar masses should undergo pair instability supernovae, where the core converts photons into electron-positron pairs, reducing the pressure and causing the star to explode completely with no remnant. Yet LIGO detected GW190521, two black holes of 85 and 66 solar masses merging, with the product being a black hole of about 142 solar masses. Both parent black holes fell in the pair instability mass gap. Something is wrong with either our understanding of stellar evolution or our assumption that all these black holes formed from individual stellar collapse. One attractive explanation is hierarchical mergers. Black holes formed in dense stellar environments like globular clusters can merge with each other repeatedly, building up mass through successive collisions. A series of mergers could produce black holes well into the pair instability gap. This would mean some of the black holes LIGO is detecting are second or third generation products of earlier mergers. This hierarchical merger scenario has implications for understanding black holes in dense environments. Globular clusters are ancient, dense collections of hundreds of thousands of stars. In their cores, encounters between stars and compact objects are common. Black holes, being the heaviest objects, tend to sink to the center through gravitational friction. There they interact with each other, form binaries, and eventually merge. The gravitational wave recoil from an asymmetric merger can kick the product out of the cluster entirely. Only the most massive and densely concentrated clusters can retain the merger products through multiple generations. The study of black holes in globular clusters has become a rich research area connected to gravitational wave astronomy. The gravitational wave population has also revealed that the distribution of black hole masses doesn't look like a simple power law. The standard prediction of stellar evolution models. There seem to be features in the distribution, peaks and valleys, that might encode information about the physics of stellar collapse. Different masses of stars explode in different ways, producing black holes of different masses, and the distribution of final black hole masses preserves information about those processes. Reading this distribution correctly is an ongoing project requiring many more detections to accumulate statistics. Understanding what black hole spin tells us is equally important. The gravitational wave signal from a merging binary carries imprints of both the magnitudes and the orientations of the individual black hole spins. Spins aligned with the orbital angular momentum produce different waveforms than misaligned spins. If two black holes form together in a binary star system, their spins tend to be aligned with the orbit because they formed from the same disk of gas. If they paired up dynamically in a dense cluster, their spins are oriented randomly relative to the orbit. The LIGO population shows both types, confirming that black holes form and pair through multiple channels. The merger rate of black holes inferred from LIGO detections, roughly a few to a few tens of events per year per cubic gigaparsec of volume, is consistent with plausible estimates of the rate of massive star formation and binary evolution across cosmic history. But the uncertainties are large because we don't know precisely what fraction of massive stars end as black holes versus neutron stars, and we don't know how efficiently binary star systems survive the supernova explosions that form compact objects. Each LIGO detection constrains these uncertain parameters a little more. While observational astronomy was making these strides, the theoretical frontier was not standing still. The information paradox that Hawking identified in 1974 continued to drive theoretical physics forward. By the 1990s, it had become clear that solving the paradox would require understanding quantum gravity, the theory that successfully unifies quantum mechanics and general relativity. String theory was the leading candidate. String theory proposes that the fundamental constituents of nature are not zero-dimensional point particles, but tiny one-dimensional vibrating strings. Different vibrational modes of the same type of string correspond to different particles. This seems like a minor technical modification, but it has profound consequences. String theory contains gravity automatically. The gravitational force emerges from the exchange of a particular vibrational mode of the string called the graviton, and string theory can be formulated consistently in ways that avoid the infinities that plague attempts to quantize gravity using point particles. In 1996, Andrew Strominger and Qumran Vafa achieved a breakthrough. Using string theory techniques, they calculated the entropy of a particular class of extremal black holes from first principles. Extremal black holes are those spinning at the maximum rate consistent with general relativity or carrying the maximum possible electric charge. They found that by counting the number of different string theory microstates that correspond to the same macroscopic black hole, they could reproduce exactly the Bekenstein-Hawking entropy formula. The entropy was proportional to the area of the event horizon, as Bekenstein and Hawking had found from thermodynamic arguments, but now it came from an actual microscopic calculation. This was profound. It meant black holes really did have entropy in the statistical mechanical sense. There were real microscopic degrees of freedom being counted. Information really was stored somewhere, not destroyed. The resolution of the information paradox had to lie in understanding these microscopic degrees of freedom. The Strominger-Vafa calculation was limited to extremal black holes in string theory, far from realistic astrophysical black holes, but it established the principle. Black holes are not simple. They have enormous microscopic complexity hidden behind their simple exteriors. João Maldacina's paper of 1997 was the next earthquake. Working within string theory, Maldacina discovered a precise mathematical equivalence between two completely different theories. On one side was a theory of gravity and strings living in a 10-dimensional space-time called anti-de Sitter space, a space-time with a particular type of constant negative curvature. On the other side was a quantum field theory without gravity, living on the 8-dimensional boundary of that anti-de Sitter space. These two theories were claimed to be exactly equivalent. Every calculation in one had a corresponding calculation in the other, and the results would match. This AD-CFT correspondence, standing for anti-de Sitter space and conformal field theory, was initially received with excitement and some skepticism. The mapping between the theories was remarkable in its specificity. A black hole in the anti-de Sitter bulk corresponded to a thermal state in the boundary field theory. The temperature of the black hole corresponded to the temperature of the thermal state. Hawking radiation from the black hole corresponded to ordinary thermal fluctuations in the boundary theory. And crucially, in the boundary theory, there was no information loss. Quantum mechanics governed the boundary theory completely. Information about the initial state was preserved throughout the evolution, encoded in the correlations of the quantum state. If the two theories are truly equivalent, then information is also preserved in the gravitational theory. The black hole does not destroy information. Whatever information falls in somehow comes back out in the Hawking radiation, encoded in subtle correlations that are not captured by the simple thermal approximation Hawking used. The paradox was resolved in principle, even if the detailed mechanism remained obscure, but Maldaceno's correspondence also raised new questions. How exactly does information escape? What happens to it inside the black hole? What is the boundary theory description of the black hole interior? Leonard Susskind had been working on related ideas through the 1990s. He and Gerard 't Hooft had independently proposed the holographic principle, the idea that the information content of a region of space-time is not proportional to its volume but to its surface area. This came directly from Bekenstein's observation that black hole entropy scales with horizon area. If you try to pack more information into a region than the maximum allowed by the holographic bound, the region collapses into a black hole. The black hole is the maximum entropy state for a given volume, and its entropy is set by the area. This suggests that space itself might be a hologram, with all the information that appears to be distributed through a volume actually encoded on a lower dimensional boundary. Susskind developed the idea of black hole complementarity to address what different observers experience. An observer falling into a black hole crosses the event horizon without noticing anything special, at least for a large enough black hole. General relativity's equivalence principle guarantees that the laws of physics locally should be the same everywhere, including at the event horizon. So the infalling observer sees nothing dramatic at the crossing and reaches the singularity some time later. An observer who stays outside sees something completely different. They never see the infalling observer cross the horizon at all. Due to gravitational time dilation, the infalling observer appears to slow down and freeze asymptotically at the horizon, their image becoming infinitely redshifted and faded. The two observers have completely different experiences, and Suskind's complementarity principle says this is fine. The two descriptions can't be simultaneously verified by any single observer, so there's no contradiction, but in 2012, Ahmed Al-Amheri, Donald Marolf, Joseph Polchinski, and James Sully published a paper that challenged this comfortable resolution. The firewall paradox, as it became known, showed a deep inconsistency in how we think about black holes and quantum information. The argument goes roughly like this. For information to be preserved in Hawking radiation, the late-time radiation must be entangled with the early-time radiation. For the infalling observer to experience smooth empty space at the horizon, the Hawking particle that falls inward must be entangled with its outgoing partner. But a particle can't be maximally entangled with two different systems simultaneously. This is called monogamy of entanglement. Something has to give. The paper proposed a radical resolution. Maybe the event horizon isn't smooth at all. Maybe there's a wall of high-energy radiation right at the horizon, a firewall that destroys anything crossing it. The infalling observer wouldn't smoothly cross the horizon and fall toward the singularity. They'd hit the firewall and be incinerated instantaneously. This would preserve quantum mechanics by preventing the problematic dual entanglement, but it would violate the equivalence principle, one of the cornerstones of general relativity. An observer in free fall at the horizon should experience nothing special. The firewall proposal said they'd instead hit a wall of fire. The firewall paradox generated enormous controversy and drove intense theoretical activity. Some physicists accepted the firewall as necessary to preserve quantum mechanics. Others rejected it and sought alternatives that preserved the equivalence principle. New ideas proliferated. Maybe the interior of the black hole is not behind the horizon but elsewhere, encoded differently in the exterior degrees of freedom. Maybe the structure of space-time near the horizon is fundamentally different from what general relativity predicts, modified by quantum gravity effects. Maybe the standard rules of quantum mechanics need to be modified for black hole systems. One of the most striking proposals connecting to the firewall debate was the ER equals EPR conjecture proposed by Susskind and Maldacena in 2013. ER refers to Einstein-Rosen bridges, wormholes connecting two separate regions of space-time, which Einstein and Rosen had described in 1935. EPR refers to Einstein-Podolsky and Rosen's 1935 paper on quantum entanglement, which Einstein had called spooky action at a distance. The conjecture proposed that these two phenomena, wormholes and entanglement, are different descriptions of the same thing. Two entangled particles are connected by a microscopic wormhole. The degree of entanglement corresponds to the traversability of the wormhole. If this is right, when a black hole is entangled with its Hawking radiation, it's connected to that radiation through a network of microscopic wormholes. The information inside the black hole doesn't have to escape through the event horizon. It's connected to the exterior through entanglement, through geometry. The resolution to the firewall paradox might be that the interior of the black hole is not behind the horizon in the usual sense, but is geometrically connected to the exterior through entanglement. This is a radical reimagining of the relationship between quantum information and space-time geometry. These ideas have taken shape under the broader research program of understanding how space-time emerges from quantum mechanics. The idea that space-time is not fundamental, but emerges from more basic quantum degrees of freedom, is now a major theme in theoretical physics. Entanglement between different parts of a quantum system seems to be related to the geometric connections between corresponding regions of space-time. More entanglement means shorter distances. Disentangled regions correspond to disconnected space-time regions. The geometry of space is a manifestation of the pattern of quantum entanglement. This research program has produced concrete calculations. Working in simplified models of black holes within ADS-FT, physicists have calculated the fine-grained entropy of Hawking radiation and shown that it follows a curve consistent with information preservation. Initially, as the black hole radiates, the entropy of the radiation increases. After what's called the page time, roughly when the black hole has lost half its mass, the entropy of the radiation begins to decrease. This is the signature of information returning. The detailed calculation requires summing over different geometric configurations, including ones with wormholes connecting the black hole interior to the radiation. When these contributions are included, information is preserved. These calculations, developed over 2019 and 2020 by Jeff Pennington, Ahmed Almheri, and collaborators, represent a major step toward resolving the information paradox. They don't answer every question. They're done in simplified settings that don't directly describe realistic astrophysical black holes. The mechanism by which information escapes is still not fully transparent, but they provide a consistent picture in which information is preserved, and they do so using calculations within quantum gravity, not just arguments from general principles. The connection between black hole physics and quantum error correction has also become clear in recent years. Quantum error correction is the technique used in quantum computers to protect quantum information from errors caused by noise. It works by encoding information redundantly across multiple physical qubits so that local errors don't destroy the information. The structure of how quantum information is encoded in the Hawking radiation of a black hole turns out to be related to quantum error correction codes. The black hole scrambles information in a way that protects it from local disturbances, the same way error correction codes protect quantum information. Understanding this connection has led to insights in both quantum computing and quantum gravity. The concept of quantum complexity has entered black hole physics through the work of several theorists, particularly Susskind. The computational complexity of a quantum state measures how many quantum gates you'd need to prepare that state, starting from a simple reference state. For a black hole in ADS-CFT, the complexity of the corresponding boundary quantum state keeps growing long after the black hole has thermalized, growing for a time proportional to the exponential of the black hole entropy. This continued growth has a geometric interpretation. The complexity corresponds to the volume of the black hole's interior, which keeps growing as the black hole ages, even after other properties have stabilized. This complexity equals volume conjecture, and related ideas suggest deep connections between the geometry of space-time and the computational complexity of quantum states. The interior of a black hole is a region of space-time where things keep growing and changing even as the exterior stays essentially constant. This growth is captured by increasing complexity. Understanding why complexity keeps growing and what it corresponds to geometrically is an active research area that connects quantum computing, quantum information, and black hole physics. All of these theoretical developments have been happening against the background of rapid advances in observational capabilities. The next generation of gravitational wave detectors is already being designed. LIGO and Virgo are being upgraded continuously with improved lasers, better mirror coatings, and quantum noise reduction techniques called quantum squeezing. The Japanese detector Kagra joined the network. The proposed Cosmic Explorer in the United States and Einstein Telescope in Europe would have arms 10 to 20 kilometers long, dramatically improving sensitivity and allowing detection of black hole mergers across much greater distances. The most ambitious project is LISA, the Laser Interferometer Space Antenna, approved by the European Space Agency and planned for launch in the 2030s. LISA will consist of 3 spacecraft flying in a triangular formation separated by 2.5 million kilometers, linked by laser beams. Free from seismic noise and with baselines millions of times longer than ground-based detectors, LISA will detect gravitational waves in a frequency band inaccessible from Earth. This band contains gravitational waves from mergers of supermassive black holes millions to billions of times the mass of the Sun. When 2 galaxies merge and their central supermassive black holes eventually spiral together and merge, LISA will detect it. The signal would be enormous, potentially detectable from any galaxy in the observable universe. LISA will also detect a gravitational wave background, the accumulated signal from all the black hole mergers throughout cosmic history that are too distant to resolve individually. This stochastic background will carry information about the merger history of supermassive black holes across cosmic time, constraining models of galaxy formation and evolution. Excitingly, a hint of this background has already been detected by pulsar timing arrays, networks of pulsars used as cosmic clocks whose timing irregularities reveal very low-frequency gravitational waves, pulsars, rapidly rotating neutron stars that emit beams of radio waves like cosmic lighthouses, are extraordinarily regular. By timing the arrival of pulses from dozens of pulsars spread across the galaxy, physicists can look for correlated timing residuals that would signal a gravitational wave background. In 2023, multiple pulsar timing array collaborations around the world independently announced evidence for exactly this background. The signal has the right frequency spectrum and the right angular correlations between different pulsars to be consistent with a background of gravitational waves from merging supermassive black holes. It's not yet a definitive detection at the confidence level physics requires, but it's a strong hint that we are beginning to hear the low-frequency universe. The Event Horizon Telescope collaboration continues to advance. Adding more telescopes improves the coverage of the UV plane and improves image fidelity. Observing at shorter wavelengths, using millimeter and sub-millimeter radio waves instead of the 1 millimeter waves used for the first images would improve resolution. This would allow imaging of smaller black holes or finer details around known ones. There are proposals to place radio telescopes in space, which would provide baselines longer than Earth's diameter and achieve even higher resolution. Such a space-based extension of the Event Horizon Telescope could potentially image the event horizon of the black hole in M87 in far greater detail, testing the fine structure of space-time near the horizon. Polarization observations have already produced stunning science. When the Event Horizon Telescope measured the polarization of light from M87's black hole, it revealed the magnetic field structure in the accretion disk. Synchrotron radiation from electrons spiraling in magnetic fields is linearly polarized, with the polarization direction perpendicular to the magnetic field. The observed polarization patterns showed ordered, coherent magnetic fields in the regions close to the event horizon. This was consistent with theoretical models where strong, organized magnetic fields are essential for launching the powerful jets from M87's black hole. Understanding jets remains a major unsolved problem in black hole astrophysics. Some supermassive black holes launch bipolar jets of relativistic plasma extending for millions of light years. These jets can heat the gas in galaxy clusters, preventing it from cooling and forming stars. They're responsible for some of the most energetic phenomena we observe. The jet from M87's black hole, which extends for 5,000 light years and ends in a bright knot called Knot A, was the first jet ever discovered when Heber Curtis observed it in 1918. But how jets form, how they're launched and accelerated to near-light speeds, and why some black holes have powerful jets while others don't, remain poorly understood. The leading model, the Blandford-Znajek mechanism proposed in 1977, involves magnetic fields threading the event horizon of a rapidly spinning black hole. The spinning black hole winds up the magnetic field lines, creating an electromagnetic field configuration that extracts energy from the black hole's rotation and funnels it into a jet. In this model, the jet is powered by the rotational energy of the black hole itself. As the jet extracts energy, the black hole spins down. This process can release enormous amounts of energy over the lifetime of an active galactic nucleus. Testing this model requires observations very close to the base of the jet, near the event horizon. The Event Horizon Telescope's imaging of M87 showed the jet base region and confirmed that the magnetic field structure was consistent with the Blandford-Znajek mechanism. But the details of how the jet is collimated and accelerated over the first few light years remain uncertain. Future observations with higher resolution and different observing frequencies will provide more constraints. The relationship between a black hole's mass and the properties of its host galaxy has proven to be one of the most surprising correlations in astrophysics. The mass of the central black hole is tightly correlated with the velocity dispersion of stars in the galaxy's central bulge, a measure of how gravitationally bound the stellar system is. More massive galaxies have faster moving stars in their bulges and more massive central black holes. The correlation is remarkably tight, given that the black hole influences only a tiny central region of the galaxy, while the stars in the bulge extend for thousands of light years. Something connects them. The favored explanation involves feedback. When the black hole is actively accreting and powering a quasar or active galactic nucleus, the energy output can exceed the binding energy of the entire galaxy. Jets, radiation, and outflowing winds from the active nucleus heat and push the surrounding gas. This can shut off the supply of cold gas to the galaxy, stopping star formation. It can even drive winds that blow gas entirely out of the galaxy. Through this feedback, the black hole regulates its own growth. It grows until its energy output is sufficient to shut off the gas supply. The correlation between black hole mass and galaxy properties emerges naturally if different-sized galaxies require different amounts of feedback to stabilize. Simulations of galaxy formation that include this AGN feedback produce galaxies that match observations much better than simulations without it. Without feedback, simulated galaxies produce too many stars too quickly and end up too massive. With feedback calibrated to observations, The simulations produce realistic galaxy populations with realistic star formation histories. Black holes aren't passive passengers in galaxy evolution. They're active participants, regulating the growth of their hosts across cosmic time. This co-evolution of black holes and galaxies must have begun early in cosmic history. The James Webb Space Telescope, launched in December 2021, is revealing active black holes at unprecedentedly high redshifts, corresponding to times when the universe was less than 1 billion years old. Some of these early black holes are already very massive, hundreds of millions to even billions of solar masses, at a time when the universe hasn't had much time to grow them. How they got so massive so fast is one of the outstanding mysteries of observational cosmology. The usual route to a supermassive black hole starts with a stellar mass black hole from the collapse of a massive star, then grows by accreting gas. But the Eddington limit restricts how fast a black hole can accrete. Radiation pressure from the hot accretion disk pushes gas outward, counteracting gravity. At the Eddington limit, these forces balance, and accretion can't proceed faster without blowing away the infalling gas. A stellar mass black hole accreting continuously at the Eddington limit for 1 billion years would reach about 1 billion solar masses. That's possible, but it requires continuous accretion with no interruptions for 1 billion years. Alternatively, these early supermassive black holes might have started from much more massive seeds. Direct collapse black holes could form if a massive gas cloud collapsed directly without first forming stars. In the early universe, conditions might have allowed the collapse of gas clouds of millions of solar masses directly into black holes, bypassing the stellar stage entirely. From a seed of millions of solar masses, reaching 1 billion solar masses requires much less growth. Identifying the seeds of the first supermassive black holes is a key goal of the James Webb Space Telescope and future facilities. The James Webb Space Telescope is also revealing unexpected populations of active galactic nuclei at high redshift that challenge our models of early black hole growth. Some of these early AGN are embedded in relatively small host galaxies, suggesting the black holes formed before their host galaxies were fully assembled. Others have outflowing winds that are beginning to shape their environments. Every new JWST observation of the early universe adds to the picture of how the first black holes grew and how they influenced the galaxies they inhabited. Intermediate mass black holes in the range of 100 to 1 million solar masses are the missing link between stellar mass and supermassive black holes. Finding them would help us understand the seeding of supermassive black holes. They're expected to exist in the centers of dwarf galaxies, in the cores of globular clusters, and as the products of hierarchical mergers. But they've been elusive. A few good candidates exist, detected through their X-ray emission or through dynamical effects on surrounding stars. Some LIGO detections might be the mergers of intermediate mass black holes with stellar mass black holes, providing a gravitational wave signature of these objects. LISA will be able to detect intermediate mass black holes, orbiting supermassive black holes, a type of event called an extreme mass ratio inspiral. Extreme mass ratio inspirals are among the most scientifically valuable sources for LISA. When a stellar mass compact object, a white dwarf, neutron star or black hole, falls into a supermassive black hole, it completes thousands of orbits near the event horizon before finally plunging in. During each orbit, it emits gravitational waves that carry precise information about the geometry of space-time around the supermassive black hole. By tracking the phase of the gravitational wave signal over thousands of orbits, LISA can map out the space-time geometry with exquisite precision. This is essentially a test of whether supermassive black holes are actually described by the Kerr metric, the solution to Einstein's equations for a rotating black hole. Any deviation from Kerr due to modifications of gravity, quantum effects near the horizon, or the presence of additional matter would show up as a departure from the expected orbital evolution. The precision achievable with extreme mass ratio inspirals far exceeds what can be done with stellar orbit tracking or black hole shadow imaging. There's also growing interest in what happens when a stellar mass black hole in spiral into a supermassive black hole disrupts the surrounding matter. If the supermassive black hole has an accretion disk, the inspiraling object will plow through it repeatedly, creating a characteristic periodic electromagnetic signal alongside the gravitational waves. Detecting both signals simultaneously would provide spectacular confirmation of the multi-messenger picture and teach us about the environments of supermassive black holes. Black holes also connect to some of the highest energy phenomena in the universe, ultra-high energy cosmic rays and very high energy gamma rays. Cosmic rays are charged particles that arrive at Earth from space with energies up to 10 to the 20 power electron volts, 100 million times more energetic than anything the Large Hadron Collider can produce. Their sources are unknown, but candidates include regions near supermassive black holes where electromagnetic acceleration can reach extreme energies. Very high energy gamma rays, above 100 gigaelectron volts, have been detected from AGN by instruments like the Fermi Space Telescope and ground-based Cherenkov telescope arrays. These gamma rays come from relativistic jets and accretion regions near black holes. In 2022, photons with energies exceeding a peta-electron volt, 1,000,000 gigaelectron volts, were detected from several astrophysical sources. The acceleration mechanism producing particles at these extreme energies is debated. Some of the sources appear to be associated with extreme environments near compact objects, including black holes. Understanding how black holes can accelerate particles to such extraordinary energies requires understanding the physics of magnetic fields, plasma dynamics, and particle acceleration in the vicinity of event horizons. The physics of magnetic fields and plasma near black holes is being explored with new simulations. General relativistic magnetohydrodynamic simulations model the behavior of hot magnetized plasma in the curved space-time of a black hole. These simulations have become incredibly sophisticated, incorporating radiation transport, pair creation, and complex magnetic field dynamics. They're used to interpret the Event Horizon Telescope observations and to understand how accretion disks form, how jets launch, and how energy flows in active galactic nuclei. The simulations require significant computing resources and are run on the world's largest supercomputers. One of the most active theoretical frontiers is the study of quantum aspects of black holes using techniques from quantum information theory. The concept of black hole scrambling refers to how information falling into a black hole gets mixed throughout the black hole in a way that looks random and thermal from outside. Black holes are conjectured to be the fastest scramblers in nature, mixing information into their degrees of freedom in a time proportional to the black hole mass, times the logarithm of the black hole entropy, much faster than most other quantum systems. Understanding scrambling connects to understanding how the black hole information paradox is resolved, because scrambling is a key step in how information gets encoded in Hawking radiation. The study of quantum chaos and thermalization in quantum systems has been revolutionized by insights from black hole physics. The Sachdev-Yekitaev model is a quantum mechanical model that was proposed as a simple example of a system that saturates the bound on chaos and scrambling. It was later recognized as a model of a black hole in one lower dimension, a connection that has been fruitful for understanding both the model and the black hole. The SYK model and related models provide tractable examples where you can study scrambling, thermalization, and quantum chaos analytically. Topological aspects of black hole physics are also being explored. The calculation of black hole entropy using replicated path integrals and saddle points that include wormholes connecting different replicas has led to a better understanding of why information is preserved. The contribution of wormhole geometries to gravitational path integrals had been considered suspect, but recent work has shown that including them is essential for getting the correct answer for the entropy of Hawking radiation. This wormhole contribution effectively connects the black hole interior to the exterior, providing a geometric mechanism for information to escape. The broader lesson of these developments is that the relationship between geometry and quantum information is far deeper than we previously appreciated. Space-time geometry isn't just a classical background, it's a dynamical quantum object whose configurations must be summed over. Different geometrical configurations, including exotic ones with wormholes and other topological features, can contribute importantly to physical observables. Understanding which geometric configurations matter and when is a key challenge for quantum gravity, semi-classical gravity, the approximation where quantum fields live on a classical curved space-time, has been pushed to its limits in these calculations. Going beyond the semi-classical approximation requires confronting the full quantum theory of gravity. Progress in this direction is coming from multiple sides. String theory provides a UV-complete quantum theory of gravity where calculations can sometimes be done exactly. ADS-CFT provides a definition of quantum gravity in terms of a well-understood quantum field theory. Loop quantum gravity and other background independent approaches provide different perspectives. The challenge is synthesizing these perspectives into a coherent picture. Experimental tests of quantum gravity effects in black holes are out of reach for the foreseeable future. The energy scales where quantum gravity becomes important, the Planck scale, are 17 orders of magnitude beyond what particle accelerators can probe. Direct tests of Hawking radiation from astrophysical black holes are impossible given the minuscule temperatures involved, but indirect tests are possible. Analog gravity systems in the laboratory mimic some aspects of black hole physics and allow testing of Hawking-like effects in controlled environments, acoustic black holes, created by supersonic fluid flows where sound cannot propagate upstream, create acoustic horizons analogous to event horizons. Experiments with ultra-cold atomic gases have observed the acoustic analog of Hawking radiation, confirming that Hawking's mechanism operates in systems far removed from real black holes. These experiments don't probe quantum gravity, but they confirm the quantum field theory calculation that underlies Hawking radiation. The phonons emitted from the acoustic horizon have been measured and shown to be thermal. With a temperature that matches Hawking's formula, optical analogues of black holes have also been created in metamaterials and other optical systems. The analog of horizon crossing in these systems can be probed in ways impossible for real black holes. These experiments are more relevant to fundamental physics than they might seem, because the mathematics describing quantum fields in curved spacetime is identical, regardless of whether the curved spacetime is gravitational or an effective curved spacetime in an optical or acoustic medium. The philosophical implications of 50 years of black hole research are profound. Black holes have forced physicists to confront fundamental questions about the nature of information, the relationship between quantum mechanics and gravity, and the structure of space-time. The information paradox shows that our most successful theories are in deep tension with each other, and that we don't yet have a complete picture of physical reality. The holographic principle suggests that our intuition about space and dimensionality is fundamentally wrong. The connection between entanglement and geometry suggests that quantum mechanics and space-time are more intimately connected than we thought. These are not just technical puzzles. They touch on deep questions about determinism, causality, and the nature of knowledge. If information is preserved when black holes evaporate, then the universe is deterministic at the deepest level. The future is uniquely determined by the past, even if that determination runs through extremely complex quantum states that we could never practically compute. If information is destroyed, then determinism fails and the future is not uniquely determined by the past, violating quantum mechanics. The resolution of the paradox will tell us something fundamental about whether the universe is deterministic. The question of what an observer experiences falling into a black hole also has deep implications. General relativity says nothing special happens at the horizon for a large black hole. Quantum mechanics and the information paradox suggest something dramatic might happen, either a firewall or something else. If the equivalence principle is violated at the horizon, then our most fundamental principle of gravity, that acceleration is equivalent to gravity, fails in the vicinity of black holes. That would be a revolutionary discovery. The nature of singularities inside black holes is equally profound. If singularities are real, they represent points where physics breaks down, where all predictability ends. Most physicists suspect that quantum gravity will resolve singularities, replacing them with something finite and physically meaningful. What that something is remains unknown. It might be a quantum bounce, where the collapse is halted and reversed. It might be a transition to a different phase of space-time. It might be a baby universe pinching off from our own. The resolution of the singularity is one of the deepest open questions in physics. Black holes have also changed how we think about the emergence of space-time. The fact that black hole entropy scales with area rather than volume, the holographic principle, and ADS-CFT all point toward the possibility that three-dimensional space is not fundamental, but emerges from a lower dimensional description. Entanglement between quantum degrees of freedom creates the geometric connections we experience as space. This is one of the most radical ideas in contemporary physics, and it emerged from studying black holes. If space-time is emergent, then the usual questions about what happens inside a black hole might be the wrong questions. There might not be a well-defined inside in the usual sense. The black hole interior might be a complicated encoding of information in the exterior degrees of freedom, not a separate region of space-time that you could physically travel to. These ideas challenge our most basic assumptions about the geometry of the world. The past 50 years have transformed black holes from mathematical abstractions to observed realities, from curiosities to the central objects of theoretical physics, from simple to extraordinarily complex at the quantum level. We've gone from debating whether black holes exist to photographing their shadows, hearing them collide through gravitational waves, using them to probe the deepest questions in physics, and discovering that they regulate the evolution of galaxies. We've learned that black holes are not the simple objects they first appeared to be. They're characterized externally by just 3 numbers, but internally they harbor an enormous amount of quantum information. They're the maximum entropy objects in the universe, packing the most information into the least space. They evaporate and return that information to the universe somehow in ways we don't fully understand. They're connected to each other and to the radiation they emit by quantum entanglement and perhaps by microscopic wormholes. Their geometry might be a manifestation of quantum information structure rather than a fundamental feature of reality. We've learned that black holes are cosmic engines. They power quasars, the brightest objects in the universe. They launch jets that extend for millions of light years and regulate star formation in galaxies. They merge in collisions that shake space-time itself and release more energy in a fraction of a second than our sun will emit in its entire lifetime. They orbit each other for millions of years before finally spiraling together. They disrupt stars that pass too close. They lurk at the centers of virtually every large galaxy in the universe, including our own. We've learned that understanding black holes requires unifying our 2 greatest physical theories, general relativity and quantum mechanics. That unification is not yet complete. The information paradox is the sharpest statement of what we still don't understand. Every approach to quantum gravity, string theory, loop quantum gravity, causal dynamical triangulations, and others must confront black holes and explain how they work at the quantum level. Black holes are the testing ground for quantum gravity. We've learned new experimental techniques that opened new windows on the universe. Gravitational wave astronomy didn't exist before 2015. Black hole imaging didn't exist before 2019. Multi-messenger astronomy combining all these channels is in its infancy. Each new technique reveals aspects of black holes that are inaccessible to the others. Together, they're building a complete picture of black holes across all their mass scales and environments. We've learned that black holes are laboratories for testing fundamental physics in regimes we can't access any other way. The strong field regime of gravity, where curvature is extreme and velocities are relativistic, is accessible only near compact objects. The information about how space-time behaves in this regime is encoded in gravitational wave waveforms, in the shapes of black hole shadows, and in the X-ray spectra from accretion disks. Extracting this information requires precise theory and observation working together. The next 50 years will likely be as transformative as the last. We're entering an era of precision black hole science where we can measure black hole properties with high accuracy and use them as precision tests of gravity. We're building detectors that will hear black holes across the universe, including the merger of the supermassive black holes that powered ancient quasars. We're developing theory that may finally explain the quantum nature of black holes and resolve the information paradox. We might discover that black holes are fundamentally different from what we think. Maybe quantum gravity effects modify the event horizon in observable ways. Maybe black holes leave long-lived remnants when they evaporate rather than disappearing completely. Maybe primordial black holes turn out to be a significant component of dark matter, solving one of cosmology's greatest mysteries. Maybe we'll find signatures of black hole physics in laboratory quantum systems, confirming the deep connection between space-time geometry and quantum information. Black holes are strange. They bend time and space. They trap light. They evaporate quantum mechanically while remaining classically eternal. They destroy information and preserve it. They're the simplest and most complex objects simultaneously. They power the brightest phenomena and are themselves invisible. They're everywhere and inaccessible. They're old. Most supermassive black holes formed billions of years ago and perpetually new to science, revealed to direct observation only in the last decade. 50 years of research have revealed their reality, their prevalence, and their importance. They've revealed their quantum complexity and their cosmic role. They've revealed that understanding them requires new physics we don't yet have. And they've revealed that pursuing that new physics is one of the most productive endeavors in science, spinning off insights into quantum information, condensed matter physics, mathematics, and computation. The black hole at the center of our galaxy, Sagittarius A, is orbiting the center of the Milky Way along with all the other stars. 4 million solar masses, invisible except for its gravitational grip on nearby stars and the faint radio glow of its sparse accretion. It's been there for billions of years, waiting for us to notice it. We have noticed it now. We've photographed its shadow. We've tracked stars whipping around it at relativistic speeds. We've understood something of its nature, its mass, its spin, its relationship to our galaxy. What we haven't done is understand what's inside it. What happened to everything that ever fell in, how the information is stored, and what it means for space and time to break down at its center. Those questions are the frontier. They'll drive physics forward for the next 50 years and beyond. Black holes are not just extreme objects at the edge of our universe. They're at the center of our understanding of what the universe is. Everything we learn about them teaches us something fundamental about reality, and we're just getting started.